There's a video, 122,000 views. It's called something like, "The Earth is Behaving Strangely, Scientists Can't Explain." It presents three phenomena as one. The core has slowed down. The magnetic pole is racing away. The Schumann resonance has gone beyond the norm. All of this is blended into a single narrative with a single conclusion. Something is happening, and no one is telling the truth. The problem isn't that the phenomena are fabricated. All three are real. The problem is that they are not connected in the way the single Earth anomaly narrative implies. Each has its own mechanism, its own timeline, its own significance. And when they are combined into one sentence, the very thing that makes science useful disappears: the ability to understand what is actually happening. Let's break them down one by one. We'll start with the core. First, some context necessary to understand everything that follows. The Earth is not a monolithic sphere. It is a multi-layered system with different physical properties at each level. The outer crust, 5 to 70 kilometers thick, depending on whether we are under an ocean or on a continent. The oceanic crust is thinner, about 5 to 7 kilometers. Under young mountain ranges, it can be up to 70 kilometers thick. The crust is rigid, cold, and brittle on a geological timescale. Beneath the crust is the mantle, about 2,900 kilometers of hot silicate rock, not liquid in the usual sense. Under high pressure, this material behaves like an extremely viscous plastic mass. On timescales of millions of years, it flows. It is on these convective currents in the mantle that the tectonic plates move. Below the mantle is the liquid outer core, about 2,200 kilometers thick, molten iron with traces of nickel and lighter elements, sulfur, oxygen, or silicon, depending on the model. Here, true liquid convection occurs. The molten metal moves in currents, heated from below by the solid core and by the radioactive decay of isotopes. This convection, combined with the Earth's rotation, creates the magnetic field through the geodynamo effect. And at the very center is the solid inner core, about 1,220 kilometers in radius. The pressure is 3.6 million atmospheres. The temperature is around 5,000 to 6,000 Kelvin, roughly the same as the surface of the sun. At such pressure, iron crystallizes despite the temperature, which is why the core is solid where, based on temperature alone, it should have remained molten. All these layers interact. The mantle presses down on the core. The solid inner core rotates relative to the liquid outer core and the mantle. Convection in the liquid outer core generates the magnetic field. Everything is connected, but on different timescales and through different physical mechanisms. The timescale for tectonic plate movement is millions of years. The timescale for geomagnetic reversal is hundreds of thousands of years. The timescale for the core's superrotation is decades. The timescale for the magnetic pole's drift is years. This is fundamentally important. The three anomalies from the news are occurring at different depths and on different timescales. They aren't necessarily parts of a single event just because they're mentioned in the same video. Until 1936, no one knew that the Earth had a solid inner core. Denmark, 1936. Inge Lehmann, a seismologist, is analyzing earthquake data from stations around the world. P-type seismic waves, longitudinal waves that travel through the Earth, were supposed to curve around the center along a predictable path according to the model at the time, which assumed the entire core was liquid. But Lehmann discovered an anomaly. Faint reflections of these waves were appearing in the shadow zone, an area where, according to calculations, they shouldn't have appeared. The only physically consistent explanation: inside the liquid core, there is a solid sphere with a different wave propagation speed. The waves were partially reflecting off its surface, and these reflections were penetrating the shadow zone. Lehmann published this idea in 1936. The paper was authored simply by I. Lehmann. At the time, a female name on a scientific publication often reduced its credibility. Confirmation came in the 1970s when global seismic networks had accumulated enough data. Inga Lehman lived to see her work recognized. She died in 1993 at the age of 104. Since the 1960s, the International Seismological Center has been coordinating a global network of stations. Every significant earthquake is an experiment. The waves pass through the entire Earth, and by analyzing the differences in their arrival times at various stations, we can reconstruct the structure of the planet's interior. By the 2000s, the archive had grown large enough to track not only the core's structure, but also its dynamics, how it moves relative to the mantle over time. 2023, Yi Yang and Xiaodong Song from Peking University publish a paper in Nature Geoscience. DOI:10.1038/S 41561-022-01112-Z. Let's open the original. The authors use a method called differential travel time analysis. They take repeating earthquakes from the same points on the planet, sources that are periodically active with the same geometry. If the inner core rotates at a different speed than the mantle, the angle at which a wave crosses the core changes over time. This alters the travel time, minimally on the order of fractions of a second over decades, but measurable with modern equipment. Yang and Song analyzed data from the 1990s to the 2020s. Their conclusion: from about the 1970s to the early 2000s, the core rotated slightly faster than the mantle, a phenomenon known as superrotation, at a rate of a few tenths of a degree per year. This had been known since the 1990s from the work of Song himself and his colleagues. Then around 2009, the superrotation ceased. The core's speed became nearly synchronized with the mantle's. It may have even begun to lag slightly behind. This is called a change in the core's superrotation speed. It is not the core stopping. It is not the core spinning backwards. Such a phrasing would imply that the Earth itself had begun to rotate in the opposite direction, with the sun rising in the west and setting in the east. The paper says nothing of the sort. This is about a fractional speed, a tiny differential between the core and the mantle. To put it in physical terms, we are talking about an angular deviation of a fraction of a degree per year. Over 20 years, this accumulates to a few degrees. It is measured through seismic wave delays of milliseconds. All the while, the core continues to complete a full rotation with the Earth, 360 degrees every 24 hours. The change recorded by Yang and Song is a change in a very small amount of speed added on top of that main rotation. The mechanism the authors propose is gravitational and electromagnetic coupling between the solid inner core, the liquid outer core, and the mantle. The system balances between different angular velocities through these forces and can cyclically change this ratio on timescales ranging from several years to several decades. This is the normal dynamics of a multi-component rotating system, not a sign of destruction. There is important context that the paper itself does not hide. Before Yang and Song's publication, there were at least 3 independent groups of scientists with different estimates for the superrotation cycle period. Some suggested 70 years, others 6 years, still others 20 to 30 years. This is normal. It's the early stage of data accumulation in a young field of observation. Direct measurements of the core's superrotation have only been conducted for a few decades. There is not enough data for a confident consensus on the cycle's period. The Royal Observatory of Edinburgh commented on Yang and Song's publication directly. There is no reason to believe that anything catastrophic is happening to the Earth's core. This is not a refutation. It's contextualization for a public that has read headlines like, "Earth's core has slowed down," and interpreted them literally. And this is precisely where we see a competitor's take on data journalism. Take the actual paper, remove the uncertainty, remove the context about different period estimates, remove the Royal Observatory's comment, add "scientists are shocked," and get 122,000 views on a topic that sounds significantly more modest in the original. This is the first anomaly. Let's move on. The magnetic pole. The Earth is a giant magnet. Not in a metaphorical sense. Literally, the planet has two magnetic poles and field lines that can be measured with a compass. This field shields us from the solar wind, a stream of charged particles that would otherwise destroy the atmosphere. It is the absence of a sufficiently strong and long-term stable magnetic field that played a key role in the loss of the Martian atmosphere. This is now the leading hypothesis, supported by data from NASA's Mars Atmosphere and Volatile Evolution (MAVEN) mission since 2014. The source of the field is the liquid outer core. Convective flows of molten iron, combined with the Earth's rotation, create a self-sustaining magnetic field through the geodynamo effect. This is not a static structure. The currents in the liquid core are constantly changing, which means the field and the position of its poles are also changing. The north magnetic pole is the point on the Earth's surface where the magnetic field vector points straight vertically downward. It has never coincided with the geographic North Pole, and it has never stood still. In 1831, James Clark Ross was the first to determine its position. The Canadian Arctic archipelago, around 70 degrees north latitude. By the beginning of the 20th century, the pole was drifting slowly, a few kilometers per year, predictably. NOAA maintains the World Magnetic Model jointly with the British Geological Survey. The model is updated every 5 years. It's built into literally everything: aviation navigation, military navigation systems, smartphones, and marine vessels. Any gadget that refers to magnetic north uses this data. In the 1990s, something changed. The pole began to accelerate. By the 2000s, 40 kilometers per year. By the 2010s, 55. Its direction, from Canada toward Siberia. A steady movement, not a chaotic one. In 2000, the pole was located approximately 1,100 kilometers north of the magnetic South Pole in a geodesic sense, on the Canadian side of the geographic pole. By 2020, it had shifted significantly, crossed the geographic North Pole, and emerged on the Russian side. The reason is a change in the convective flows in the liquid core. A group from the University of Leeds, led by Philip Livermore, published an analysis in 2018 showing the specific mechanism. A redistribution occurred between two convective vortices in the liquid outer core. One, under the Canadian sector of the Arctic, weakened. The other, under Siberia, strengthened. This altered the configuration of the magnetic field in the polar region and pulled the pole eastward. January 2019. NOAA announces that the World Magnetic Model is being updated ahead of schedule, a year early. The official reason: the pole had shifted so rapidly that the current model had exceeded the acceptable limits of error for navigation systems in the high latitudes of the Arctic, where the angular effect of the pole's shift is at its maximum. Naval and aviation systems operating on Arctic routes received the updated data. This was a specific administrative decision prompted by a specific physical change. No conspiracy, an engineering problem. The data had exceeded its accuracy limits sooner than expected. The practical consequences are real, not apocalyptic. Airports periodically rename their runways. Runways are numbered according to their magnetic azimuth. Runway 36 means a heading toward magnetic north, 360 degrees. When the pole shifts enough, the azimuth changes, and the runway gets a new number. This happens at high-latitude airports several times a decade. It's a routine operation that requires repainting markings and updating documentation. Compasses still work. GPS does not depend on the magnetic field. Smartphones receive the correction automatically. Now separately, the South Atlantic Anomaly. This is a region over the South Atlantic and South America where the magnetic field strength is anomalously low compared to the global average. The ESA launched 3 swarm satellites in November 2013, specifically to measure the Earth's magnetic field with unprecedented precision. Data from SWARM shows that over 200 years, the field in the region has weakened by about 9%. The anomaly is expanding and shifting westward. Within it, a second spot of weakening has appeared in recent years, over Chile. This is not an officially confirmed split of the anomaly into two. It is an emerging structure that is being observed and studied. The practical effect is specific. February 3rd to 4th, 2022, SpaceX launches 49 Starlink satellites into an orbit of about 210 kilometers, the standard parking orbit before they raise themselves to their operational altitude. During this time, a geomagnetic storm occurs, caused by an intensified solar wind from a solar flare on January 29th. The storm heats the upper layers of the atmosphere. The atmosphere expands. The air density at an altitude of 210 kilometers increases sharply compared to the calculated parameters. Aerodynamic drag increases. 40 of the 49 satellites are unable to overcome the drag and raise their apogee. They deorbited, burning up in the atmosphere. The storm came from the sun, not from the South Atlantic Anomaly. But the anomaly is not neutral. A region with a weakened field means that high-energy particles from the solar wind penetrate deeper into the atmosphere over this sector, intensifying the heating. SpaceX adjusted its strategy for subsequent launches. A sign of an impending geomagnetic inversion? Geophysicists are cautious on this matter. The weakening of the field in the South Atlantic is a separate regional process with a measurement history stretching back to the 1800s. The last major inversion was the Matuyama-Brunhes event, about 780,000 years ago. The Lechamp event, 41,000 years ago, was an excursion. The field weakened and was disrupted significantly, but a full inversion did not occur. It lasted about 1,000 years. There is no data on a mass extinction directly linked to this excursion. The average time between inversions is 200,000 to 300,000 years, with a wide variance. Inversions don't happen on a schedule. The fact that the last one was 780,000 years ago doesn't mean we are overdue. Geology doesn't work that way. The next inversion? Statistically, it's a matter of tens to hundreds of thousands of years, not in the coming decades. That was the second anomaly. Let's move on to the third. The Schumann resonance. 1952. The German physicist Win Schumann publishes a theoretical calculation. An electromagnetic cavity exists between the conductive surface of the Earth and the lower edge of the ionosphere, a layer of ionized gas at an altitude of 60 to 100 kilometers. Like a hollow resonator, like a guitar body that amplifies certain frequencies, only here the body is the space between the Earth and the ionosphere, and the strings are electromagnetic waves. In this cavity, standing electromagnetic waves should arise at frequencies for which the wavelength is a multiple of the Earth's circumference. The first resonant frequency is about 7.83 Hz. The harmonics, 14.3, 20.8, 27.3, 33.8 Hz. This was experimentally confirmed by Schumann himself, together with Herbert Koenig in 1954. Since then, it has been measured many times and is well described. The source of this resonator's excitation is lightning. Across the entire planet, at any given moment, there are about 40 to 50 lightning strikes per second. Each discharge generates a broadband electromagnetic pulse, an extremely low-frequency signal that propagates around the Earth and excites the resonant cavity. The main sources of thunderstorm activity are tropical regions, Central Africa, the Amazon, and Southeast Asia. Each has its own daily and seasonal activity pattern. Now, about the spikes up to 80 Hz. Let's break it down specifically. 7.83 Hz is the average base frequency. It varies naturally. Daily fluctuations, 7.6 to 8.0 Hertz. Different levels of thunderstorm activity in different parts of the planet at different times of day create a slight shift. Seasonal variations. They exist. This isn't a case of the norm being violated. This is the normal behavior of a nonlinear system excited by random sources of varying intensity. High-frequency peaks, up to 80 Hertz and higher. These are higher harmonics in short-term discharges. Powerful storm cells in the tropics, especially mesoscale convective systems, multi-cell thunderstorms, clusters of thunderstorms, generate short-term electromagnetic pulses that cover a wide range of frequencies. At Schumann resonance monitoring stations, such peaks are seen regularly. They directly correlate with the intensity of thunderstorm activity in tropical regions. This has been well known and documented since the 1970s. This isn't an anomaly, it's atmospheric electrical physics. And the third key point, the Schumann resonance is a phenomenon in the lower atmosphere, at altitudes of 0 to 100 kilometers. The Earth's magnetic field is generated at a depth of 2,900 to 5,100 kilometers in the liquid outer core. The solid core is at a depth of 5,100 to 6,371 kilometers. A physical mechanism that would directly link spikes in the Schumann resonance to the state of the core or the main magnetic field has not been described in any peer-reviewed paper. These are different systems at different depths with different physical mechanisms. When the media writes, the Schumann resonance went beyond the norm at the same time as anomalies in the core and magnetic field, this is correlation without a mechanism, not proof of a connection. There are countless correlations in nature. Most of them are not causal. For example, in the 1990s, the drift of the magnetic pole accelerated, the USSR began to collapse, and the internet became widespread. Concurrence is not a mechanism. A mechanism must be described, measured, and tested. That is the third anomaly. More precisely, it is not an anomaly. It is the normal behavior of the atmospheric resonator, described, measured, and explained back in the 1950s. Before moving on to the analysis, here are two additional contexts that usually don't make it into media narratives. They help to understand why these three phenomena, specifically, became candidates for being combined into a single anomaly. First context, the history of science communication on the topic of the magnetic field. Geomagnetic inversion is a beautiful topic. It's intuitively understandable. North and south swap places. It has geological traces. In rocks formed during different polarities, the magnetization is oriented differently. You can show this in a picture. It's easy to explain in 30 seconds. Since the 1990s, when the pole's drift began to accelerate, the topic has periodically come up in pop science. Is an inversion happening right now? Is a good headline. No, probably not, but we can't give a guarantee because we have insufficient data on the mechanism, is a bad headline. The media chose the first option. Scientists in their comments provided the second. This is the standard gap between the scientific process and its media representation. Yang and Song fell into the exact same trap 3 decades later, but this time with the core. The core has slowed down is a good headline. A change in the rate of superrotation within a presumed multi-decadal cycle, the mechanism of which is still being studied, is not a good headline. The result? A viral wave of publications with a completely rephrased conclusion. Second context, the practical importance of each phenomenon and why it differs. The core. The change in the rate of superrotation is a field of fundamental geophysics. There are no practical consequences in the coming years. It is important for understanding the physics of the planet. It has no applied significance on human timescales. The magnetic pole. There are real practical consequences: navigation, satellite orientation, protection from solar wind in the polar regions, but they are manageable. NOAA, the British Geological Survey, and ESA deal with this systematically. These are operational engineering challenges that can be solved. The South Atlantic Anomaly. This is more significant in practical terms for satellite operators in low-orbit systems. Starlink 2022 is a clear example. As the number of satellites in low orbit increases, this becomes more relevant. It requires inclusion in the calculations for every launch. The Schumann resonance. Practically neutral in the context of the threats being discussed, monitoring it is useful for studying lightning activity and climate, but not for assessing the state of the core or the magnetic field. This is an important distinction that is completely erased in the three anomalies of Earth narrative. Now for a new framework. This is structure D, a known story, the point where everything is different, the consequence, and what now. The known story. Three phenomena combined into a narrative of the Earth is acting strange, scientists can't explain it. The point where everything is different. Each of these phenomena has been described, measured, and published in peer-reviewed journals with specific authors, methods, data, and conclusions. None of these conclusions contain the words catastrophe or unexplained. Yang and Song write about a change in the speed of superrotation. Livermore writes about a change in convective vortices. Swarm records a weakening in a specific region. Schumann described a resonance that works exactly as it should. The consequence. The single anomaly narrative is not a description of reality. It is an editorial decision to take three different phenomena, find a common theme, Earth, remove the nuances, remove the specific mechanisms, remove the timescales, and get an audience that feels threatened. 122,000 views. What now? This is where a question arises that goes beyond geophysics. When anxiety unites unrelated facts better than precision separates them, it creates a problem in the distribution of attention. Not metaphorically, literally. A viewer who already knows about the three-part Earth anomaly considers the topic closed. They get it. There's no reason to read further. There is no incentive to figure out which of the three phenomena actually requires monitoring, which doesn't, and on what time horizon. But further is where things with real timescales are found. Apophis 2029. On December 27, 2004, astronomers Roy Tucker, David Tholen, and Fabrizio Bernardi discovered an asteroid. The probability of a collision with Earth on April 13, 2029 was 2.7%, a record high in the history of asteroid tracking, level 4 on the Torino scale. The media paid attention for a few days. By 2006, refined data had ruled out a collision in 2029. The probability dropped to 0. But the flyby will happen. On April 13, 2029, at a distance of 31,600 kilometers from the Earth's surface. This is below the orbits of geostationary satellites, and this close flyby will alter Apophis's orbit, creating a keyhole, a narrow region of space which, if entered during the 2029 flyby, will set the asteroid on a collision course for 2036. This is a real, measured, documented chain of events with specific dates and specific physics. December 27, 2004, another event. The magnetar flare SGR 1806-20. In 0.2 seconds, a magnetar star approximately 50,000 light-years away released more energy than the Sun does in 250,000 years. The flare ionized the Earth's ionosphere on the night side. Changes were recorded in the Global Geomagnetic Monitoring System. This is documented. If this magnetar were 10 light-years from Earth, it would have been the end. NASA does not include this class of phenomena in its public lists of priority threats. Both events are real. Both are measured. Both require understanding, because understanding provides the ability to assess risks adequately. Mixing three unrelated anomalies into a single catastrophe doesn't just misinform. It occupies the space in one's worldview that should be occupied by something more precise. A viewer who already knows about the Earth will not seek out information about the Apophis keyhole or the energetics of magnetars. The slot is filled. In summary, the inner core. Yang and Song, Nature Geoscience, 2023. The core's super-rotation changed speed around 2009. It is presumably part of a multi-decadal cycle. Three groups of scientists give different period estimates: 6, 20 to 30, and 70 years. This is normal for a young field of observation. No stopping of any kind. Royal Observatory of Belgium. No cause for alarm. The magnetic pole. The drift has accelerated since the 1990s to 55 kilometers per year. A real, documented phenomenon. NOAA issued an unscheduled update to the World Magnetic Model in 2019. The pole is moving towards Siberia due to changes in convective flows in the liquid core, a specific mechanism described by Livermore and colleagues in 2018. Practical consequences: recalibration of navigation systems. Not catastrophic. The South Atlantic Anomaly, ESA swarm, a 9% weakening of the field over 200 years. Real consequences: 40 Starlink satellites were deorbited in the February 2022 storm. A sign of a reversal? Unknown. Statistically, the next reversal is tens to hundreds of thousands of years away. The Schumann resonance, a fundamental frequency of 7.83 Hz plus harmonics, the normal physics of the Schumann atmospheric resonator. Spikes up to 80 Hz are from tropical thunderstorms. There is no mechanical link to the core or the main magnetic field. Three phenomena, three independent mechanisms, three independent timescales. The question that remains open is not about the Earth. It's about how we process information that requires separation, not unification. The media rewards unification. One narrative, one alarm, one topic, more views. Science rewards separation. Three different phenomena, three different conclusions, three different practical consequences. The difference between these approaches is not about how interesting a video is to watch. It's the difference in what we notice and what we miss. Names, data, documents. This is not a mystery. These are three different phenomena. Each requires its own analysis, and that is precisely why they are mixed into one. In September 2015, the LIGO detector registered the first gravitational wave signal in history, a discovery that would win the 2017 Nobel Prize in Physics. But 150 days passed between the moment of detection and the public announcement. 1,000 scientists across the globe knew. Not one of them said a word. Not in an interview, not in private correspondence, not even by accident. In those 150 days, the detector had already caught a second signal. In our next video, we'll explore how this silence was maintained, who made the decision to delay the news, and what happens to a science that keeps secrets not for the sake of conspiracy, but as a matter of methodology.